I'm going to make some comments on the formula. In the formula, you need three things, of course. You need the lower limit, the upper limit, an interval. We're going to use a few questions, use many questions to talk about how to use the formula. At the end of the class, if we have time, I'm going to tell you why the formula is true using infinitesimal method. Okay. But we concentrate on how to use the formula first. You imagine there's a solid. It may not be a cone. It could be a potato. It could be anything actually. Okay, any solid. To use the formula to compute the volume of the potato. So this is not a potato, of course, or whatever solid. All we need is three things: an interval. The interval you project. Now listen to me, okay? You project the solid onto either x-axis or y-axis, so you have an interval. Later on, we are going to practice a few questions showing you the meaning. And the integrand a of x is called the cross-sectional area, the area of the cross-sections. I will tell you the meaning, okay? Project the solid onto the interval. You have project the solid onto x-axis. You have an interval, and then passing through x for any point x on the interval. You choose an arbitrary point x on the interval. Okay. You imagine you use a plane perpendicular to x-axis. I want to repeat. You use a plane perpendicular to x-axis to cut the solid. You have a cross section. Now look at the mouse cursor. You have a cross section. This must be done for any x, for every x. For every x, you use a plane perpendicular to x-axis to cut the solid. You have a cross section. A cross section is a plane region as a two-dimensional thing. For the cross section, we can talk about the area. A of x is the cross-sectional area. It's the area of the cross-section. The value of a of x depends on the location of x, right? For different values of x, for different location of x, the cross-sectional area is different. As long as you can get the area of all the cross-sections for all values of x, then you integrate the cross-sectional area from A to B. You have the volume. I hope it's not too hard to understand. You integrate areas, cross-sectional areas, and then you are going to get the volume. So that makes sense? You integrate all the cross-sectional areas from A to B, you have the volume. Okay, we're going to repeat many questions showing the idea. Okay. Of course, the similar formula is true if it's easier to project if it's easier to get the cross-sectional areas if you cut the solid using the planes perpendicular to y-axis. So, and correspondingly, there's another formula. Another formula is something like this. The volume V is equal to, so now let's say from C to D, A of y, and then dy. So here A of y is the cross-sectional area of the cross-sections perpendicular to y-axis. From past years, I know that this section is easy for some of you guys, and this section is not so easy for many of you guys. So because you do need to imagine everything in 3D, in three-dimensional. Okay, we're trying to compute the volume. a solid is a three-dimensional stuff. You need to imagine the thing in space. Okay, now the first question I want to go over is this is actually the first question on the handout. Okay. Yeah, probably I'm going to make the question a little bit simpler. Okay. The curve we're going to use. I'm not going to use a general number a. I want to use a particular a value to talk about how to compute the solid. I will show you what I mean. Okay. Now the curve, I'm going to replace the curve with a particular a value. Now let's say we do a value of 2, so the curve, it becomes y equals 4 minus x squared. If you can do that, then the general case is easy too, right? So it's less abstract. Okay, so before we move on, anybody know this curve? Now let R be the plane region enclosed by the curve and the x-axis. Now anybody know the graph of this curve? So probably we did not mention that in Math 101, but you should learn that in high school. You should have learned that in high school. Okay. Okay, I will give you a little bit hint. So anybody know the graph of this curve? So maybe you can try to answer my question one by one. Okay. So what is the shape of that curve? X squared plus y squared equals 4. So just tell me a name. You can type the name in the message. What is that curve? You know that. Trust me, you know that. Okay, you learned that in high school. That's a circle. That's a circle. More precisely, that's a circle. If you did not know that, or if you don't remember that, that's a circle centered at the origin. Centered at the origin with the radius of. To describe a circle, you have to tell me the center. You have to tell me the radius. Centered at the origin. Now, can you remember the radius? What is the radius of the circle? The radius is 2. Okay. You know that. You learned that. I'm pretty sure you learned that in high school. I know conic sections are not in BC curriculum, but you know this curve. You learned this curve. That's a circle. Now, we're going to use that to make the connection. Now we can talk about. Now look at the mouse cursor. We're going to talk about what is that curve. From that equation, you solve the equation for y. Okay, you solve the equation for y. You have y squared equals 4 minus x squared. I meant you solve the equation for y. Y squared is equal to 4 minus x squared. To get y, you take the square root. In general, you get plus or minus square root of. To take square root, when solving the equation, you have plus or minus. Okay, y equals plus or minus 4 minus x squared. Okay. I mean, the whole circle now can be represented by y equals plus or minus square root of 4 minus x squared. Now, in the question, if I omit the negative sign, so what would be the meaning of that function? If you omit the negative sign, the geometric meaning of the graph of that function is the upper half of the circle. So that makes sense? Y is always positive. Y is always positive. We omit the lower part. Okay. In any case, I'm going to sketch the plane region first. Okay. The plane region is bounded by a curve and the horizontal axis. I just told you this curve is upper half of the circle. Okay. In any case, we need to sketch the plane region first. Okay. In the first step, we sketch the solid. Okay, or imagine the solid. Again, that's the upper half of the circle centered at the origin. Centered at the origin. I'm not going to draw the y-axis. Center at the origin. So that's that point has x-coordinate of 0. Okay, with the radius of 2. The radius is 2. So now let's say 2 is here. On the other side, you also have a negative 2 in here. The graph of that function is upper half of the circle. Okay. I'll try to make it a little better. Illustration only. That's the upper half of the circle. I was trying to draw a circle. Okay. Okay, now let's get the solid. Okay. Now we are trying to compute the volume of something. So the plane region R is enclosed by upper half of the circle and the horizontal axis. I don't know if I should do some shading, but if I do shading later on, the thing could be a little messy. But what I meant is the entire plane region. Okay, the entire plane region. Can I say a disk, upper half of the disk? Okay. Now I want you to imagine, I told you everything is going to be in space. Everything is three-dimensional. Now I want you to imagine. Still, I want to remove the shading. Now that's the plane region R. Okay. Now I want you to imagine, or you can take a piece of paper, cut off a half circle. Okay. Now I want you to rotate the entire plane region R around horizontal line, horizontal axis. Then the whole thing will trace out a solid. Anybody want to tell me, give me a description of the solid? In the question, we want to rotate the plane region R around the x-axis. We are going to have a solid. Anybody want to tell me the solid? Give me the description of the solid. The entire plane region, you rotate the entire plane region around horizontal axis. You have a solid. Probably I'm going to make the line a little bit longer. Okay. And the label X. No, that's not hemisphere. That's the entire sphere. That's the entire sphere. You rotate the region around. Yeah, that's right. Yeah, that's right. You rotate R, the upper half of the circle, around x-axis. You just use a piece of paper, okay, and then you cut half a circle, and then you rotate half a circle around one diameter. So can I say that way? And then you have a sphere. Okay, a sphere. Okay. And by the way, the sphere is something like this. Sphere, right? Actually, that's not hollow. It's the solid sphere. The solid sphere. So can I call the solid sphere a ball? Actually, there's a difference between the two terms. Strictly speaking, there's a difference between two terms. A sphere, it means the surface, a surface. Okay. A ball in math is a solid thing. Okay. Actually, we're talking about the ball. There's nothing wrong to say a sphere. It doesn't matter. Okay, you have the sphere. So the entire solid is going to be something like this. Again, illustration only. It's hard for me to draw stuff on computer. Okay. In any case, we identify the thing. Identify the solid first. Okay. And then I'm going to give you the step procedures for computing the volume of the solid. I know for for the sphere, you learned the formula in high school, how to compute the volume of a sphere, right? But now you imagine you did not learn that formula, or you can imagine using calculus we can compute the volume of many more complicated stuff, or you can imagine we can use calculus to tell you why the formula is true. Okay. And probably later on I'm going to talk about the general form, why we have the formula for computing the volume of a solid. Okay. Using calculus to compute the volume of a solid, we divide the whole procedure into some steps. Okay. So the steps so will tell you how to get the interval, how to get the value of A, how to get the value of B, okay, and how to get the area of every cross-sectional area. Okay. The first thing first, how we get the interval. Okay. To get the interval, you imagine we project the solid. Use your common sense to understand what I mean by project. Okay. We project the solid onto x-axis. By that we mean you imagine the x coordinates of all the points in the solid in what range. We get the interval. If we project the entire solid onto x-axis, we get the interval. Anybody want to tell me the interval? The interval is going to be the interval on which we are going to do the integration. You have a line, and then you have a sphere from -2 to 2. Yeah, that's right. That's right. We project the solid, the entire sphere, onto x-axis. We have an interval from -2 to 2. Or you can imagine the smallest possible value of x is -2. The largest possible value of x is +2, right? So that's how we get the interval. The interval is the interval from -2 to 2. Do not lose track. The formula we are going to use is that formula. Okay, is that formula. Now we know the interval. We got the interval. Okay. Secondly, actually more importantly, it's okay. Make the solid a little bit three-dimensional. The solid is something like this. Right. Secondly, we are going to get A of x. In most cases, this is the harder part. Okay. I'm going to introduce a new notation. So basically, the following notation is standard in math. Okay. It can save you writing many words. Okay. Yeah, probably you have seen the notation before in high school or other courses. So anybody want to tell me the meaning of this notation? Yeah, probably you have learned it before. It means for every, okay, for every, for each, for all, the same thing, for every. Okay. Now, again, we're trying to get the areas of all the cross sections for every x. Okay. Now you imagine x is here. X actually the following argument is true for any x on the interval from -2 to 2. No matter where this x is, the following argument is true. Okay. The new notation, okay, for every x in the interval, so that the standard notation in the interval from -2 to 2. Probably I mentioned the notation before in Math 101. Okay, that's the notation in set theory. Okay, the meaning of the notation is for, I'm going to read the meaning again, for every x in the interval from -2 to 2. Okay, you imagine x is here, and probably I'm going to make the location of x at a different location. Okay, I just make x here. I think that's okay. Now let's recall the meaning of the cross section. Okay, now let's recall the meaning of the cross section. The cross section determined by x. You imagine, okay, you use a plane. You use a plane. I said a plane, not the aeroplane, of course. You use a plane perpendicular to x-axis and passing through this point. I want to repeat, you use a plane perpendicular to the horizontal line, x-axis, and passing through this point to cut the solid. What is the cross section? Anybody want to tell me? Give me a description of the cross section. Again, I want to use a plane perpendicular to the horizontal axis and passing through this point to cut the solid. What is the shape of the cross section? Okay, you imagine you have a potato and you use a knife. The potato is super round, or watermelon, super round. Okay. No, that's not a hemisphere. You use a plane region to cut. Okay, you just slice a watermelon. The whole thing is the whole watermelon. You just imagine the whole thing is a watermelon. Okay, and then perpendicular to x, you use a knife to cut, passing through this point, and perpendicular to x-axis. So what do you get? What do you get? So tell me again. Try again, please. Circle, a smaller circle. Yeah. A circle. Actually, a circle, right? Again, you imagine the whole thing is a watermelon, and then you use the plane is a knife. Okay, you use a knife to cut the watermelon. You have a circle, right? You have a circle. Okay. Okay, for each x in between -2 and 2, the cross section perpendicular to x-axis is a circle. It's a circle, right? In order to get the area of the circle, we need the radius. We need the radius. We need the radius. To identify the radius, I'm going to use another way to describe the circle. I'm going to use another way to describe the cross section. Now listen to me carefully, okay? Now listen to me carefully. You draw a line segment of that. Sorry. It's a little messy. I was trying to make it better. It's getting worse. You draw a line segment, something like this, okay? Passing through point X, you draw a line segment perpendicular to x-axis. And then you rotate the line segment. You rotate the line segment around x-axis. Follow me, okay? You have a circle. You rotate the line segment around x-axis. I know why some people told me hemisphere, half circle or something. You need to rotate the whole way. The whole way, all the way. You need to rotate the line segment all the way around x-axis. You probably all the way, so not only halfway. Okay. You rotate the line segment all the way around x-axis. You have a circle. That circle is actually the cross section. That circle is a cross section. Okay. So temporarily, I'm going to call the radius of the circle r of x. So because it depends on the location of x. Okay. Now try to understand r of x is actually the radius of the cross section. R of x is actually the radius of the cross section. Okay. You rotate the line segment around horizontal axis all the way. You have a circle. R of x is the radius of the circle. So that is the cross section, right? Now we are going to get the area of the circle. So before getting the area of the circle, you need the radius. Okay. So with the radius, I still use r of x to denote the radius. Anybody want to tell me very quickly what is the radius? No, it's not 2. It's not 2. The whole radius is 2. The radius of the total square, the total sphere is 2. So this one should be smaller, right? Now look at the mouse cursor. If the x value is at the origin, if x is the origin, then the radius is 2. Now x is here. X is here. X can be at any location in between -2 and 2. I will tell you what we mean. Okay, it's probably a little too early for me to ask that question. Okay. Now let's figure out the coordinates of this point. Okay. Now let's figure out the coordinates of that point. I do not want to label that point. Now look at the mouse cursor. Okay. Now we are trying to figure out the coordinates of that point in terms of x. Okay. Of course, x coordinate is x. So what is the y coordinate? You remember upper half of the circle has the equation of, I'm going to label on the other side. Upper half of the circle has the equation of y equals square root of 4 minus x squared. This point is on the circle. Now look at the mouse cursor. This point is on the circle. Okay, x coordinate is x. What is the y coordinate if x coordinate is x? How can we represent the y coordinate in terms of x? Y coordinate is so because upper half of the circle has the equation square root of 4 minus x squared. If we know x coordinate, then y coordinate is computed in terms of x as 4 minus x squared. So does that make sense? Yeah, that's right. Yeah, that's right. Okay. It's comparable to the following. Okay, it's comparable to the following. On the parabola, if x coordinate is 2, what would be the y coordinate on the line? If the curve has the equation y equals x squared. If x coordinate is 2 and the point is on the curve, what would be the y coordinate? So in this case, it would be 4. So the point has the coordinate 2, 4, right? It's comparable. It's comparable to that. Upper half of the circle has the equation square root of 4 minus x squared. If I give you x coordinate, now x can be any number. I have to use x in here. Okay, and then how can we get the y coordinate in terms of x coordinate? You use the equation of the function. You use the representation of the function. You have the y coordinate. Okay, you have x in here. Now my question. Now let's go back to my question. Okay, now I'm looking for the radius of the circle, the radius of the cross section. We mentioned the cross section. The entire cross section is a circle. The entire cross section is a circle. You use a knife to cut the solid at the location of x. The cross section is a circle. Now I'm looking for the radius of the circle. What is the radius of the circle? So does that make sense? The radius of the circle is actually the y coordinate. That's the length of x. This is the length of y. That way, vertically you have the length of y. This is the radius of the circle. So does that make sense? With the radius, okay, finally we have the radius. So the radius is actually square root of 4 minus x squared. Okay, at this point I'm going to that's actually the key. As long as you have this, then the whole thing should be easy to compute. Okay. Now the whole thing we are trying to you are given upper half of the circle and the horizontal axis, upper half of the circle and the horizontal axis, they enclose a plane region. The plane region is upper half of the circle, the solid circle. Okay, and then we rotate the whole solid circle around all the way around horizontal axis. You have a sphere, right? Now the formula we are going to use to compute the volume is the following. We got the interval first. Okay, to get the interval, we project the solid onto x-axis. We have an interval from -2 to 2. You just imagine x coordinate is ranging between -2 and 2. So that's how we get the interval. Okay, and then for each value of x on the interval, x can be anywhere in between -2 and 2. Okay, we get the area of the cross section. The cross section is obtained by you imagine we use a plane perpendicular to x-axis to cut the solid. You imagine that's a potato, okay, or watermelon. I said, right? That's a watermelon. You use a knife to cut the solid perpendicular to x-axis. The cross section is a circle. we need the area of the circle, we need the area of the cross section in order to set up the integral, right? To get the area of the circle, the cross section, we need the radius, right? We just mentioned the radius is actually because this point is on the circle. If I give you x coordinate of the point, then the y coordinate of the point is determined by the equation of upper half of the circle. Y coordinate of this point is just the radius of the cross section. So that makes sense? Okay, for each value of x on the interval of the cross section perpendicular to the x-axis is a circle with the radius of that. After getting the radius, we are ready to get a of x. Its area, I mean the cross-sectional area. So maybe I'm going to write the full term. So the cross-sectional area let's try to write cross-sectional area. The notation is a of x. A of x is the area of the cross section perpendicular to x-axis and passing through this point x. Okay. You know the area of a circle, right? Pi r squared, right? Pi times r of x, the whole thing squared. So this is the area of the circle, right? So the cross-sectional area is pi times you take the square of r, 4 minus x squared. Any questions so far? Any questions so far? The second step is actually the key step, a harder step. Okay. After getting the area of the cross section, we are ready to set up the integral. So the volume is equal to you integrate the area of the cross section or the cross sectional area from negative 2 to 2, from negative 2 to 2. Okay, you integrate the area of all the cross sections or the cross sectional area for every x, and then you have the volume. Now the integral we plug it in. Okay, we compute the definite integral from negative 2 to 2 to 2, the definite integral from negative 2 to 2. Okay, you can leave out the constant of pi, right? And then you have 4 minus x squared. The integral is super easy to evaluate. I'm not going to do that. The main thing we are going to concentrate is to set up the integral. Probably I'm going to include the general case if I replace 4 with a on your assignment. So later on I'm going to make some comments on the assignment. Okay. That's the first question we did. Any questions about this? If you don't have any questions, we'll move on to work on a harder question. Okay. We'll move on to question 4. We concentrate on 4b first. In 4a, we compute the area. So that's the topic we did the last time. Now we concentrate on 4b. Okay. This question is harder to some of you guys. So, but don't worry, I will get you over this. The question is pretty famous. It's actually a question from a famous textbook, James Stewart. That's the most famous calculus textbook. We used to use that, but I'm trying to save you $200. We're using open textbook. Okay. Try to understand the question. Okay. The first thing is easy. We sketch the plane region first. We sketch the plane region first. Okay. The plane region is the graph of that function. The graph of that function is a parabola. It's a parabola. Okay. The graph of that function is a straight line. These two functions are easy. I will try to make the sketch a little better. Okay. The whole parabola is something like that. Now look at the mouse cursor. The whole parabola is something like that. The straight line is something like this. We just need the region enclosed by the curve and the line. Okay. The region enclosed by the line is something like that. Right. That is the plane region R. That is the plane region R. Okay. Don't be dizzy. We are going to rotate. We are going to rotate the plane region R around horizontal axis, around X axis. Now I want you to, if you are confused, cut a piece of paper in that shape. Cut a piece of paper in this shape. Okay, in this shape. Maybe I'm going to make the whole thing a little bigger. Okay. Cut a piece of paper in that shape. And then you try to rotate the plane region R. You rotate the plane region R around horizontal axis. Imagine the solid. Imagine the solid. I want you to imagine the solid. So don't worry, you don't need to work too hard to imagine it. I have a little video. I used to use Maple to show people the shape of the solid, but I think we don't have license anymore. After that, I made a video. Here's my Math 102 handout number 2. It includes the... can anybody confirm you can hear the sound? That's computer sound. I just want to make sure I set it up properly. You can hear the sound, huh? Again, so this the Maple file, the Maple program is designed to help you to understand the solid. Okay. Questions we work in class. We are going to use Maple to visualize all the geometric figures in part 2, question 4. First of all, R is the plane region bounded or enclosed by two curves. One curve is the parabola with the equation of y equals x squared. And the second curve is actually a line. We are so familiar with the shape of the two curves. So the Maple sketch of the plane region is here.
it is the plane region enclosed by the parabola and the straight line, right? Now let's imagine the shape of the solid in question B. In question B, the solid is obtained by rotating the plane region R above or around the horizontal axis. So here is the plane region R, right? It's enclosed by the line segment, the green line segment, and the part of the parabola, the red part of the parabola, right? If you rotate the plane region R around horizontal axis, so what shape do we get? Now let's imagine the shape this way, okay? If we rotate the green line segment around the horizontal axis, I think it's easy to imagine we get a cone. And the cone is something like this. So here is the line segment, right? And you rotate the line segment around the horizontal axis. You have a cone like this.
Now you see
straight
it,
cone.
right?
And then you imagine if we rotate part of the parabola, the red part of the parabola, around the horizontal axis, what do we get? We get a curved cone. Okay, it's a curved cone. I'll show you the shape using maple. Okay. Here is part of the parabola, the red part, right? If we rotate the red part of the parabola around the horizontal axis, we have a curved cone like this. Try to see it in 3D. Now, what is the shape of the solid in question 2? The solid, I think now it's easy to imagine. The solid is actually the solid enclosed by the straight cone and the curved cone. The shape of the solid is like this. Sorry. The outer surface is the straight cone in green, right? And the inner surface is the curved cone in red. In C, the plane region is the same.
Okay, so you got the shape? I think you got the shape. I made the video very slowly and I think it's pretty clear. I probably had code that day. Okay. I don't remember. I think I had code that day. Okay. So basically the whole thing, the whole solid, you rotate the entire R around the x-axis all the way, okay. The whole solid can be imagined as the solid enclosed by a straight cone and a curved cone. I think it's not too hard to imagine. Okay. At least you cut a plane region R in that shape, and then you try to try to rotate around x-axis. You can have the shape. Okay. Now we are going to use calculus to set up an integral for the volume of that solid. Okay. This point is the origin. Of course, it has the coordinates of 0. So this point, anybody want to guess the coordinates of this point? It's super easy to guess. We do not solve the system. For this one, we do not have to solve the system. It's a common point on on that curve and on that line. This point has coordinates of 1, 1. Okay, easy, right? Now we concentrate on the main thing. Okay. I'm not going to sketch the solid, okay, but you imagine the solid. For the entire thing, I'm just going to use the plane region. Okay. Again, the formula we are going to use is here. We need to identify 3 things. The interval. In many cases, the interval should be easy to identify. The interval, okay. You project the solid onto x-axis. The solid after rotating the plane region R onto x-axis. We get. Anybody want to tell me the interval, please? I mean the largest possible value of x, the smallest possible value of x. That will give you the range. 0, 1 is right. The interval from 0 to 1. From 0 to 1. Okay. Using your common sense to understand projecting, we project the solid onto x-axis. We get the interval. Okay. So that point is 1. The next part is to get the cross-section. Imagine the shape of the cross-section. Okay. We imagine the shape of the cross-section. You do something like, I might need a little bit more space, so can I skip? Can I squeeze the second step kind of in here? We start from here. Okay. This notation, it means for every x in the interval from 0 to 1. Again, this notation is for every, that notation you just imagine is in. Okay. For every x in that interval from 0 to 1. Let's imagine x is here. R is kind of in the way. I will make the notation R in here. Okay. For every x on the interval, we need to imagine the shape of the cross-section and get the area of the cross-section. I will try to tell you how to think. For each x, the cross-section, the meaning is you use the plane passing through this point, and the perpendicular to x-axis to cut the solid. That is the cross-section. I'm trying to define the cross-section in different way. Okay. Passing through this point, you have a line segment. Vertical line segment. I hope it's not too hard to understand. The cross-section is actually obtained by rotating that line segment around x-axis, around the horizontal line. Again, you rotate the line segment, vertical line segment determined by the value of x. You rotate that line segment around x-axis, the horizontal line, all the way. That's the cross-section. Anybody want to tell me a description of the cross section? The description of the cross section. So maybe I'm going to try to draw the cross section in 3D. Okay. Anybody want to tell me a description of? It's not circle. It's not circle. Actually, it's in between two circles. Okay. Still, I'm going to remove the 3D stuff. You imagine you rotate the line segment around x-axis. I will tell you the term. Okay, it's a washer. Anybody know a little bit of plumbing? No matter you know or not, you have washer. It's kind of from the bigger circle, you take out a small circle, right? If there's a leak, you replace the washer. So yeah, that's washer. Okay. Donut is good. Donut is good. Cat. Donut is good. But a very flat donut. A very flat donut. Okay. You have a donut, right? You rotate that little line segment around horizontal line. You have a washer. Can I just say washer? Actually, the method is called the washer method. Its official name, washer method. That's how we have the term washer. Washer is something like that in two dimension, right? Again, the cross section is obtained by rotating that little line segment around the horizontal axis. You have a washer. Okay. In order to get the cross-sectional area, we are going to get the area of the washer. To get the area of the washer, we need to identify the radius, two radius, right? For each x on the interval, the cross section, we have just seen the cross section. Perpendicular to x-axis is a washer. Again, the same as before. We are going to identify some points. Okay. I will identify that point first. Okay. So this point has x coordinate of x and the y coordinate of. Anybody want to tell me y coordinate? If I give you x coordinate, the point is on the curve. The curve has the equation x squared. The curve has the equation x squared. Okay. The line has the equation y equals x. If x coordinate is x, so does that make sense? The y coordinate is x squared. So because the point is on the curve, right? And likewise, for this point has x coordinate of x. If x coordinate is x, what is the y coordinate? Please. The line has the equation that y equals x. Any point on that line, x coordinate and the y coordinate are the same. So does that make sense? Y coordinate is also x. Again, you rotate the little line segment around horizontal axis, you have the washer. Now we are going to compute the area of the washer. A washer has inner radius and outer radius. A washer is something like this, right? To draw it in one plane. A washer has an inner radius and outer radius. Okay. Now I want you to tell me the inner radius and the outer radius. A washer with the inner radius I'm going to use small r of x to denote the inner radius. So can we identify the outer radius first? It's probably easier. Okay. With the outer radius, I'm going to use uppercase r of x to denote the outer radius. Anybody want to tell me the outer radius? Outer radius? Now follow my mouse cursor. Outer radius is the entire length from this point to x-axis. So that makes sense? The outer radius is from this point, x-axis, all the way until x-axis. Anybody want to tell me the outer radius? Outer radius, please. X. As a washer with outer radius of outer radius as x in terms of x. Everything is going to be in terms of x. Okay, and the inner radius Yeah, that's right. Inner radius x squared. Okay. Again, you rotate that little line segment around horizontal line, you have a washer. The washer is something like this. The outer radius is that length. The inner radius is that length. Okay. The outer radius is you rotate that line segment. The line segment from this point to x-axis. You rotate the longer part. You have the outer radius, right? Outer radius is from this point to x-axis. Inner radius is from this point to x-axis. Y-coordinate of this point will give you outer radius. Y-coordinate of this point will give you inner radius. I'm running this very slowly. I know this thing is hard to some of you guys, but probably it does. Okay, we identified the inner radius and the outer radius. Okay. Now look at the whole thing. The cross section perpendicular to x-axis is a washer with outer radius. We got outer radius, and we also got inner radius. Okay. Actually, the thing we need is the cross-sectional area, the area of the cross-section, the area of the washer. I did not say anything wrong. I said the same thing 3 times, the same meaning. So the cross-sectional area the area of the cross-section is A of x. Okay, that's the thing we need in the integral. The cross-sectional area, if you have something like this, you know the outer radius, you know the inner radius. How do you get the area in between? You subtract the area of the small circle from the area of the larger circle. You have the cross-sectional area. So that makes sense. So you have pi times upper r of x, uppercase I mean r of x, the whole thing squared, minus pi times the inner radius, pi times lowercase r of x, now the whole thing squared. We're going to plug everything in. Okay, everything is going to be in terms of x. Eventually a of x is going to be a function of x. Okay, so you have pi times uppercase r of x is the same thing as x, pi x squared, minus pi times the inner radius squared, pi times x squared squared. Can I just write pi times x to the power 4? Now we have the area of the cross section, the cross sectional area. That's what we want in step 2. I know in most cases step 2 is a little bit a longer procedure. Okay. For the people who don't know, I have been recording lecture classes. If you don't fully get it, there's a link on D12. I'm going to post this class in particular for sure, because this one is probably hard for some of you guys. Okay. In step 3, after getting the cross-sectional area, after getting the interval where we integrate the cross-sectional area from 0 to 1, we have the volume. Okay, so that's the formula. I mean, the volume is computed using the integral from 0 to 1. Okay, the cross-sectional area. I will give the whole thing in 2 steps. From 0 to 1. In brackets, you have pi times, that's my pi, x squared minus pi times x to the power 4, integrate. The integral is super easy to compute. Pi is a constant, everything is a power function, right? I will stop here. Now look at questions 4C. In 4C, you have the same plane region. Actually, the plane region bounded by a parabola y equals x squared, and a straight line y equals x. Okay. And then, so this time we are going to use the washer method. Now you know the meaning of the washer. Right. We are going to use the washer method to find the volume, or to set up the integral for the volume of the solid obtained by rotating R around a different line. In question B, I believe we rotate R, the plane region, around x-axis. So this time you rotate the plane region R around this line. This line has the equation that y equals 2. Y equals a constant is a horizontal line, right? I think I'm muted. You can hear me. You are hearing me. Okay. Now I want you to imagine the shape. Take a few seconds to imagine the shape. I will show you the video now. Okay. I will show you the video. Now I'm talking about the solid, the space, the space shape in question C. Okay. I think I did not turn on this volume. Ready?
Right. In C, the plane region is the same. Just the line of rotation is different, or the rotation axis is different. The rotation axis in C is the horizontal line y equals 2. Right. Here you have the plane region R. This part is the plane region R, right? And the horizontal line is the line y equals 2. It's a horizontal line, so somewhere in here. You imagine you rotate the plane region R around the horizontal line. What shape do we get? The shape we are going to get is is something like this. The plane region R is here. The rotation axis is the horizontal line here. If we rotate the plane region R around the rotation axis, we have a solid like this. Right? Very similarly, the solid in question D.
Okay, I think you got the idea. Okay, so this time you kind of have a hollow ball. Okay, can I say that way? In any case, I believe you can imagine the solid. Okay. I'll try to move the thing down a little bit to see. Again, so this time the line of rotation is y equals 2. So that's horizontal line. The line above the plane region R. I'm not going to label R. Okay. Probably I can label R at this location. I don't need. Okay. On this side, you're going to have a circle, something like this. On this side, you're going to have a bigger circle. So just imagine you rotate the plane region R around a line above the region. Okay. Okay, we'll repeat the step procedures for this question. Okay. Step 1 is kind of the same thing. Okay. Not for each. Step 1 is to get the interval. We project the solid onto x-axis. We always project the solid onto the horizontal axis or vertical axis. Okay. We have an interval. We have the interval. I believe it's not too hard to imagine the interval. It's still the interval from 0 to 1. Again, the bottom line is to think what's the smallest possible value of x, what is the largest possible value of x coordinate, I mean. Okay. You know, the second step is the key step, the longest step. So the interval, the integral is going to be taken from 0 to 1. So that's 0. So that's 1. Okay. And by the way, the scale of my two axes are different. Okay. What do we do in the second step? The setup is always the same. You choose an arbitrary point x on the interval. The interval you got in step 1. For each x, for every x on the interval from 0 to 1. The following argument is going to be true for any x in between 0 and 1. I will take x in here. Okay. Now you imagine the cross section. So first of all, you imagine the solid, the 3D shape, and then you imagine the cross section. The cross section, it's not too hard to understand. The cross section is also a washer, right? The cross section is also a washer. I will try to use a different way to let you see the washer so that we can identify the inner radius and outer radius. Still, you take that little line segment passing through x for the plane region. Okay, for the plane region, passing through x, you use a line to cut the plane region. You have a little line segment. you rotate the little line segment around that horizontal line. Now look at the cursor. Around the horizontal line y equals 2. Around the horizontal line with the equation y equals 2. You have a washer. So basically, you rotate this point, you have a circle. You rotate this point, you have a bigger circle. This will give you the inner radius and the outer radius. Okay. We still need the coordinates of the point. Okay. Now let's recall this point is on the parabola y equals x squared. So this point has x coordinate of x and y coordinate of x squared. This point has x coordinate of x and the y coordinate is also x. So because the line has the equation y equals x, right? Now, so later on I'm going to tell you a little more. You guys are smart. Anybody want to tell me the outer radius? I will write some wording first. Okay. So the cross section perpendicular to x-axis is again a washer with the outer radius. So this time it doesn't matter which outer radius and the inner radius, the difficulty is the same. We identify outer radius first. Okay. Okay. You rotate a little line segment around a different line, around y equals 2. Anybody want to tell me outer radius? Write something in the chat, please. So don't be scared. It's okay to write something wrong. Outer radius is actually the distance from this point to the line. The distance from this point to the line, it's not x squared. X squared is here. Okay. I will tell you the meaning, okay? Outer radius is this length. This length is 2, so that makes sense. This length is x. I'm trying to, sorry, it's a little too high. What would be that length? That length is outer radius. Close, Chad. X squared minus 2. It's not 100% right. It's close. It's getting closer. The distance from, now look at the cursor. The distance from the top line, the upper line, and the horizontal axis is 2. And the outer radius we need is actually the distance between this point and the line of rotation. My question is, what is outer radius? I hope it's not too messy, but I'm going to draw something, okay? 2 minus x squared is right. 2 minus x squared is right, Ben. The inner circle is something like this, right? The outer circle is something like this. The whole thing is a washer. Sorry, it's really hard for me to draw this thing properly, but I think you got the idea. 2 minus x squared is right. Okay, if you look at this picture, it's is 2 minus x squared. Okay, so that's the outer radius. Inner radius. Inner radius. I'm going to use lowercase r to denote the inner radius. Try again. Anybody want to tell me the inner radius? Two minus x. Inner radius is 2 minus x. I think you got it. The harder part is over. The hard part is over. We know the whole thing is the cross section is a washer. We got the inner radius. We got the outer radius. Now we are ready to get the area of the circle, the area of the washer. Okay. So the cross-sectional area A of x is the difference between the areas of two circles. Okay, outer radius is 2 minus x squared, so you have 2 pi times 2 minus x squared, now the whole thing squared, pi r squared, right? And then pi times the inner radius, the whole thing squared, 2 minus x, the whole thing squared. Okay. That is the cross-sectional area. After getting this, you just integrate the cross-sectional area from 0 to 1. From 0 to 1, and then you have the answer. Okay. So the volume of the weird solid, is obtained by integrating A of x from 0 to 1. You just plug everything in, so you have the answer, right? Again, the integral is not too hard to compute, but I just copy everything in. Okay. I'm not going to evaluate the integral.